Okay, so we saw in the last video the intuition we could have about how Schumacher inspired itself from Shannon to prove its theorem, and so we're gonna see more in details about its proving two lemmas. So just to remember, in a way, um, we have this from Shannon that we did not write. We should proofs follow from classical results from Shannon, which is this one. So Shannon says this in a way. The proof was pretty of x1 believing in as a typical the atypical strings. Is equal to 1, and so the fact is what we had before is the trace of row x or n in the quantum case by the corrector n and epsilon just equal to the sum of x1 to xn. I'm just equal to 1 to xn, believing it to tn epsilon of lambda x1 to lambda xn. And so at the left we have the quantum trace, at the right we have the sum of classical probabilities of having a typical sequence. And so this just finally is more the definition of the probability of x1 going to xn, believing into the atypical strings, So because Shannon proved it into the classical case, it is already alright in the quantum case. And the second step that Shannon proved, so in a way we have this, which is also equal to 1. Because it's simply this. And second step is that Shannon proved we have Tn epsilon is inferior to 2 to the power of n of Ha as epsilon, and it implies, let's say it implies the dimension as a typical subspace. As a epsilon typical subspace, and such that theorem of epsilon is equal to Tn epsilon. The typical strings of 2n Ha plus epsilon. Yeah, it's just basically saying that the cardinal of the number of elements into the sets is just a total number of strings, total number of sequences, different atypical strings, epsilon typical strings, and yeah, that exists. So less or more also combination that have 800 rows and 200 ones. And so the infer symbol just say that the Shannon theorem guarantees that this number of strings will never depass the exponential an exponential number of it. So yeah, and the link with the quantum dimension is the quantum subspace. As its quantum typical subspace, Vn epsilon is just constructed by taking the basis of the quantum states that correspond to those classical centers. So in a way, it's just less or more. It's equal to the number of classical channels because um, the quantum state like takes this the base of those quantum states correspond to those classical channels, and so yeah, that's why we have this equality, and like you have this that is equal to this, and um, and by this, and we have the following. So now we can like go into um, yeah, maybe I'll do another video.